Oops, sorry. I put stop on the video instead of pause. That's okay though. It was a great place to stop anyways, because we went from solving the moments acting around, or actually for all of the forces and all of the moments and making sure they all added up to 0. And now we can solve for each individual member. So now, instead of looking at the truss more as a whole and the forces, how they work on them, we're looking at each individual member. So let's start with joint A, this guy right over here. Okay, at joint A, the sum of all of the forces vertically must equal 0. Okay, so we start sum of all of the forces vertically must be equal to 0, because we have point A and this RA, we figured out RA, that's the whatchamacallit, where's my cheat sheet that I made for us? Aha, here it is. RA is the reaction at the support of A, and we figured out that was, if you remember, 225 newtons. So RA, if we're back on this page here, is equal to 225 newtons of reactionary force. So point A, for both members A, B, and AC, we need to figure out how much force is pushing back down into the ground. Okay, so, oh, sorry, we already did that. We need to figure out how much is acting in and out of point AB and AC. In order to do that, we need to take the force, the Jedi force, the force that is acting in member A, B, and we need to multiply it by the sine of 30 degrees. Sine of 30 degrees. And what does that give us? That gives us, or sorry, that is equal to a resistance of, in the opposite direction of our RA, which is 225 newtons. So the other side of this equation, whatever this is, must equal to 225 newtons. Because all of the forces, whether it's the ones acting from B into A or anything in the vertical direction going down this way, must be equal and opposite to our 225 newtons. So this equal and opposite is the stuff acting up this way, and this must equal it acting down this way. So that is what we're doing to calculate AB. We need to figure out what is exactly the opposite on the vector of this angle. So that's why we use sine 30. So if we solve for this, boop, 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 type it into our little calculator, we're going to get FAB is equal to 450 newtons. And congrats! Guess what you just solved for? Yeah, let's see if I can get the camera to see the rest of this here. AB. We have FAB, the forces on AB is 450 newtons. We could go ahead and write that down there. 450 newtons. Okay, that's your first one. I know there was a lot of explaining in the process, but the equation is not all that more complex than anything else you would have done in trigonometry in grades 8, 9, 10, 11 so far. It's just applying it to a real world situation where, as an engineer, you will be doing this, maybe through more advanced programs, through Fusion 360. You're going to be looking at a whole lot more forces, but the base knowledge of how you can use trigonometry to calculate trusses, this is what you do. This is what you do. Okay, let's take a look at point AC. So point AB, we're working kind of downwards in the vertical direction. Point AC, it's completely horizontal. So it's going to resist in the horizontal direction. So in order to solve for this, we have our equation, which is capital sigma, the forces in the horizontal direction, must equal to what? Must equal to that big fat capital zero. All right, so our equation now would be F, the forces, acting on AC, because we're replacing the sum of the forces acting, is equal to the forces acting in AB cosine 30 degrees, which must equal to 450 cosine 30 degrees. Okay, if you're like, whoa, you just got way ahead of yourself here. Why are there two equal signs? Okay, so FAC, what we can do is substitute in our FAB equals cosine 30. Because we've already figured out the first one. We figured out AB. So all we need to do, because all of these forces are basically a ratio compared to all of the other ones. So FAC would be exactly the same as saying FAB cosine 30 degrees. And guess what? We already solved for FAB. So what we can do is we can input 450 right here. I should do some brackets to do this properly. We can input 450 for FAB because we already solved it right here. I should underline this. Okay, so that remains all that we have left to solve is 450 cosine 30. And we'll put it into our calculator. Boop, 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 boop. And what that gives us FAC, or the forces of member AC, is equal to 389.71 blah 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 blah, repeating. We'll stop at 2. And our units, never forget your units, we are measuring in newtons. All right, look at that. That is 2 members solved. We know AB, we know AC. So we can write AC down 389.71 newtons. Way to go. You're like halfway there. Okay, all of the first ones that we had to do, really, these are the most difficult. After that, we have so much information that we can start filling in a lot of the questions that we have for the other points. So we're going to figure out all the forces acting upon the members that are connected with joint C. So our equation, joint C, we have 450 newtons acting down upon it. So we know we're working in the vertical direction. So we have our capital sigma. So the sum of forces acting vertically must equal 0. Really? The odds. It's almost like all of our equations are all the same and they all must equal 0. Wild stuff. Okay, so we can determine, because there is 450 newtons acting downwards upon C, that if we're calculating for member BC, the forces on BC must equal to 450 newtons. Because if we have the force acting this way, we must have an equal and opposite force acting this way. So boom, BC, 450 newtons. Okay, and yeah, now we need to figure out CD right here. And you know what's crazy is that because we have the same amount of force acting in the middle, and we know that both of these are identical in length because these angles are the same, this becomes quite easy to solve. We know that the sum of the forces horizontally, so the sum, capital sigma, of the forces horizontally acting on this node must equal to 0. And if we're looking at the forces acting on member CD, that must equal to exactly the same as the forces acting on AC. So the forces acting on AC, if we bring it up, 389.71. Oh, there goes the bell. My time's over. So 389.71 newtons. At this point, if you have equal and opposite sides, there's not a whole lot more to calculate. You just need to know that it's the same and the forces are the same. So that's at joint C. Okay, moving on. Now here's another one that is kind of simple, a little bit more tricky in this one. Joint C was probably the easiest because it's very square. There's not a lot of angles to calculate. So let's go to the next page and look at joint B. Oop, get all the calculations there. Move that to the side. All right, joint B. Okay, so joint B we have right here. So we know the sum of the forces horizontally must be equal to 0. So we've got to always, on every node, we've got to work horizontally, we've got to work vertically. So let's start with horizontally. So the sum, capital sigma, of the forces horizontally must equal to 0. And we know that we are trying to figure out, first let's figure out BD. So the sum of the forces, the forces acting in BD, we need to multiply it by the cosine of 30 degrees. Is this looking familiar? We might find something very similar in you can't see that. Something very similar in a truss where all of the sides and angles are the same and everything is like mirrored side to side. You're going to start to see the similarities start to pop up as you do your equations, but it's important to check. So we know that FBD needs to be multiplied by the cosine of 30 degrees. And this can be rewritten because we know we have 450 newtons acting down on it. Means 450 multiplied by the cosine of 30 degrees. We also need to add it because on this member there are multiple forces acting upon it. So we have 450 newtons at the cosine of 30 degrees plus an extra 450 newtons at the cosine of 30 degrees. Okay, a little bit more complex, that one. Okay, but if we're breaking it down, we need to find FBD, and all of this stuff kind of cancels out. If we get rid of cosine 30 degrees here, because we can divide it on this side, get rid of it here, we can get rid of it here, and that means that FBD is equal to what's left? Add 450 plus 450, 900 newtons. 900 newtons. We've got FBD. FBD, 900 newtons. Let's add that to our paper. Oh, we're almost done. FBD, 900 newtons. Okay, we have one more to go. Can you stick with me? We can do this. We can do this. We are almost there. All right. Okay, we did joint B. We're on to joint. What am I doing? We already did joint C. I need not joint C. Joint D. Joint D. All right, we're on to joint D, our last and final joint. So, what's the formula? Can you guess? Ooh, V capital sigma to the forces in the vertical direction are equal to a big fat whopping 0. So, we know that we have 450 newtons working in the vertical direction. So we're going to do 450 is equal to, so we've got the force acting on BD, which we know that that member is 900 newtons. BD, 900 newtons. 900. And then to get the CD, which is our last one, we would have sine of 30 degrees because we're getting the sine of 30 degrees to get CD from BD, which we already do know. So we're going to do the sine of 30 degrees. Wonderful. Okay, and then we do the math, and we get, oh, what am I doing? 450. We know that that is 450, but well, this should be C. The force on CD, which we think it's going to be the same as oh, what am I saying? Words. We think it should be not the same as, I'm tripping over my words here. Okay, the force of CD. If we do our calculations, I don't know why I got confused there. I apologize. We'll redo that. Okay, the force is acting on the member CD is going to equal to 900, because that's the force is acting on BD, around point D, is going to be sine 30 degrees. So we're going to do 900 sine 30 degrees. And we go on our calculator, which means that F to the CD is going to be equal to 450. 450. Put our units in there. We have some newtons. Newtons. My apologies. I think I'm doing this wrong. I did all of them right from here on out, and now I'm doing this one wrong. Getting all confused here. So the forces in the vertical direction, I think we need to go back to our first page. Forces in the, yes. So our forces in the vertical direction is equal to 450 newtons. So that's why I had 450 at first. equals 900 sine 30 degrees. So we've got 450 is equal to 450 newtons. That's our forces. They all balance out. We're good there. So now we need to make sure the forces in the horizontal direction also equal to 0. So forces, sum of the forces horizontal equal 0. And then we're going to get forces in the horizontal direction. We had 900, because that's our forces in BD. This time we're going to do the cosine of 30 degrees is equal to $389.71 plus 389.71. So why did we get these numbers? Well, if we go back to looking at our forces in the horizontal direction, the sum of the forces horizontally equals 0, we summated that each member in the horizontal direction has 389.71 newtons. Or the forces opposing in the horizontal direction had 389.71. And so this member has needs to kind of deliver a force in the opposite direction to oppose our horizontal direction forces acting this way. And on this side, it needs to oppose the forces acting from this side. So we have two forces acting from either side on this member. So pushing both of these ways. So we have two of those. So we need to add those together, which we have, if we do 900 cosine 30, it's going to equal to 779.42. Going to be equal to 779.42. So they all equal each other. Perfect. That's what we want. Everything equals 0. This was kind of our way to just double check that joint CD was indeed the same as point AC. We kind of had to operate under the assumption that they were because we thought they were. So we're able to write down our final one for point CD is going to be 389.71 newtons. All right, we've solved for all of them. Way to go, team. Okay, if you're still struggling to make sense of this, drawing things out for each kind of section of the problem for each joint is really, really helpful. So why don't we kind of rewind? We'll start from the point we worked on just last and kind of draw all of these diagrams out. I'm a very visual learner. These things help me. So I like to draw a little diagram when I'm going. So here, if we're drawing for point D, we have a fixed point. And we have one truss is going up in this direction, one member is going up in that direction. So we have, from the joint, we have a force of 389.71 newtons. 389.71 newtons, pushing this way. We also have a force of 389.71 newtons going in that same direction. From the top here, we have 900 newtons. Oh, and we should put what these actually are. So this is HD. So the horizontal forces at point D are pushing this way. We have the forces acting in CD are pushing that way. We have the forces acting in BD And we have the forces acting vertically. 450 newtons. So this is all the stuff acting around point D. And we have an angle of theta of 30 degrees. Beautiful. This also helps us recognize when we are working things out what direction kind of things we're pushing in, so that we know whether to write things in tension or compression. Because that is the one thing that we're missing from our results. I just put in the raw numbers, but we didn't actually say which ones are in tension and which ones are compression. Which way are they pushing? So the way we calculated it, and I should have done this as we were going along, when we were kind of looking at the vector of direction, deciding whether we were going to use cosine or sine, we should have been recognizing that and putting the arrows in. So if we have the forces in BD are pushing down on point D, we know that that's compressing because they're pushing together. So BD is going to be 900 newtons in compression. Okay, and then for CD, we have it pulling away from point D. So completely the opposite, because we have 389.71 pushing inwards. We have 389.71 of force acting in the member towards the center. Again, that's where we got those two adding together. So we need to show that that is in tension because it's being pulled away from the joint. So CD is 389.71 newtons in tension. Hopefully you're able to figure out the other ones. So BC in the middle, we have all the force going down. It's being pulled away from the top point, point B. So that's another one that's going to be in tension. AC, if we kind of go back, let's actually go and draw. Let's go and draw some of these other ones. Let's go right back up to the top with point A. So I've drawn them. Hopefully it'll help you make sense of them. So we have point A, which is a rolling joint. And we have it going this way and going that way. Da, da, da. We have in this direction pushing into the joint. We've got FAB. And FAB we figured out to be 450 newtons. And then being pulled away from this rolling point here, we have FAC, which FAC we figured out to be 389.71 newtons. We had an angle of theta of 30 degrees. What other things do we know? We know that the reaction at the support, this fella right here, we calculated that to be 225 newtons. That's R at point A. This is point A. Should circle that. Wonderful. And so, having this all drawn out, hopefully that is helping you as we've gone along, which ones are pushing in which direction so that we can figure out what each of these are doing. So we kind of look at this. We've got FAB, the forces in AB. They're pushing down towards point E. They're being squished together. Taking this member, pushing. So that would be in compression. You guessed it right, compression. All right, how about AC? So AC, we have FAC is being pulled away from point A. So that is going to be in tension. Okay, let's do that one last drawing for point. Let's see. Oh, I should have drawn joint A on this side. We can fix that later. Let's draw at point C, because that's the last one that we really need to, or we could do point B as well. Let's draw all of them. That would be fun. So at joint C. So joint C is the middle guy right here. So we have kind of a cross, and this is going to be point C. And from here going down, we have 450 newtons. We have in this direction, we have CD. And then in this direction, we have FAC, which we know FAC to be 389.71 newtons. And then in this direction, we have FBC, which we know that to be 450, yes, 400, I wrote it down over here, 450 newtons, because we've got to have an equal and opposite reaction, 450 newtons. CD is 389.71 newtons. And I hope you can appreciate all of the symmetry of like, okay, so if we have a point C right here, if we have stuff pulling in this direction, that means the stuff pulling in that direction needs to be exactly opposite. If we have stuff pulling down, that means the force that's also being pushed upwards needs to be opposite. So it's all the same. All right. Let's do that last one. Let's draw point B. That's this one right here. This one's a fun one because it's the top. Okay, so we have point B right here, and then we've got coming down, and we've got it coming down in that direction. We have a vector force being applied that way, which is 450 newtons. From a horizontal plane here, we have an angle theta of 30 degrees. FBC, this is point B, is pulling down in 450 newtons. We have FAB, which is pushing up with 450 newtons. We've got FBD, let's push up that way. FBD, which is pushing up with 900 newtons. 900 newtons. So we've got all our pretty little drawings there. Yeah. Okay. This video went over all of the calculations to do truss number 1. The really, really important thing is you remember the formula. That all of the sum of the forces in the members, all of the sum of the moments around the joints needs to equal 0. And from there, a little bit of trigonometry. Awesome. Well, thanks for watching. I'm going to do another one. It'll come out soon. All right. Thanks for tuning in. All right. Good luck.